DuckDB under the hood, Module 3. 2 queries, same table, same filter, both return 4 rows, 13 milliseconds, 668 milliseconds, same 4 rows, 50 times the difference. Why? That's this module, Columnar storage and row groups. DuckDB under the hood, Module 3, Columnar storage and row groups. Most databases store your table as rows. One row is a unit. Every column for that row lives together on disk. If you want just one column, say revenue, you still have to read the entire row to get it. DuckDB doesn't do that. It stores each column separately, all the revenue values together, all the age values together. When your query touches only one column, DuckDB reads only that column's bytes and skips everything else. That's the core idea. You've seen it in the table scan operators projections list. Now let's look at how it's physically laid out. A DuckDB table is split 2 ways at once, vertically by column. Each column is stored separately, horizontally into row groups. Each row group holds about 122,000 rows. Think of it like splitting a spreadsheet into pages, except each page is about 122,000 rows thick. So a 100 million row table splits into roughly 814 row groups. Each row group has its own copy of each column's data for that slice of rows. Why does that matter? Each column within row group gets a tiny index, just 2 numbers, the minimum value and the maximum value in that slice. That index is called a zone map. Here's why those 2 numbers are powerful. You're looking for the row where C1 equals 500,000. DuckDB checks the zone map for each row group. Group 0, min0, max about 122,000. Can 500,000 be in there? No. Skip it. Group 1, min about 122,000, max about 245,000, skip. Group 2, Group 3, all 813 of the first row groups, skipped in microseconds, never touched. Group 4, min 491,000, max 614,000. 500,000 is inside that range. Read it. That's your 13 millisecond query. 813 row groups skipped, 1 row group read, 4 rows found. Now for the 668 millisecond query, column C2 is random. Every row group for C2 has a min near 0 and a max near 100 million. 500,000 is inside every single range. Nothing can be skipped. 0 row groups skipped. All 814 read. That's the entire 50x gap, explained in 2 numbers per row group. Let's build the table. 2 columns, C1 and C2 both big int, 100 million rows. We're inserting 100 million rows. The C1 expression, I bitwise and not 3, zeros the 2 lowest bits, so every group of 4 consecutive values of I maps to the same C1, nearly sorted. C2 multiplies by a large prime and mods by 100 million, a hash scramble, effectively random. These 2 distributions are deliberate. C1 is storage friendly, C2 is not. The insert takes about 45 seconds to complete. Let's verify the storage order. The row ID virtual column shows the physical position, the actual slot on disk where this row lives. Row 0, 1, 2, 3 all have C1 equal to 0. That's the bitwise expression. Zeroing the 2 low order bits means 4 consecutive integers all mapped to the same value. Rows 4 through 7, C1 equals 4. Rows 8 through 11, C1 equals 8. Every group of 4 rows shares one C1 value, and those groups go up in order. The storage order and the value order are identical for C1. Now look at C2. Row 0, 0, row 1, 83 million, row 2, 67 million, row 3, 51 million. There's no pattern, no correlation between where the row lives physically and what value C2 holds. That's the entire difference between a 13 millisecond query and a 668 millisecond query. Let me run explain analyze on the first scan. Filter on C1, the sorted column. 1 operator, a table scan. The filter is C1 equals 500,000. 4 rows returned. Look at the timing on the scan. 13 milliseconds to search 100 million rows. That is not a cache hit. The table was just inserted. DuckDB evaluated the filter against the zone map of each row group and skipped 813 out of 814. Only 1 row group was worth opening. That is what a sorted column buys you. The min and max of C1 in each row group are tight, contiguous intervals. The target value falls inside exactly one of them. Same query shape. Now filter on C2, the randomly ordered column. Same plan shape, same table scan operator, same filter. 4 rows returned. But look at the per operator time, nearly 8 seconds of worker thread time. Wall clock total was about 2/3 of a second. DuckDB parallelized across cores, so wall time is less than the sum, but every row was still read. Nothing was skipped. The zone maps for C2 hold wide, overlapping ranges. The random scramble means every row group could contain the target value. The filter had to be evaluated against each row individually. Same query engine, same plan shape, 50 times slower. The only difference is sort order. Here is what that looks like measured. The sorted column scan finishes in 13 milliseconds. The random column scan takes 668 milliseconds, 51 times slower. Same query engine, same operator, same table. The only difference is whether the zone maps can skip row groups. Let's look inside the storage. DuckDB ships a built-in function that exposes its internal row group metadata. Let me walk through the columns. Row group ID, which of the 814 row groups this segment belongs to. Column name, which column, C1 or C2. Segment ID, there can be multiple segments per row group per column if the data is large. Start, the physical row ID where this segment begins. Count, how many rows are in this segment. Compression, uncompressed here. For our integer columns, DuckDB chose not to compress. Different column types and patterns trigger different compression strategies. And stats, that's the zone map. Look at row group 0, column C1, segment 0, mean 0, max 2044. Two numbers. Segment 1, min 2048, max 34812. Each segment of each column in each row group has these two numbers. Has updates is false everywhere. We haven't modified any rows. Persistent is false. This table lives only in memory. Both of these become important in Module 7 when we look at what happens after a heavy update. DuckDB reads these stats before it reads any actual data rows. That's the check that decides skip or read. Let's group that up to see the two-dimensional layout clearly. Row group 0, C1, about 122,000 rows, C2, about 122,000 rows, row group 1, same, and so on through 813. This is the two-dimensional layout made concrete. Each row group is a horizontal slice. Each column name is a vertical slice. The intersection, a column within a row group, is the unit that gets a zone map. 2 columns times 814 groups, 1628 column segments. Each one has a min and a max. The entire skip logic for this 100 million row table fits in 1628 pairs of integers, a few kilobytes of metadata for a table that's hundreds of megabytes on disk. The stat string is awkward to parse raw. Here's a macro that unpacks it into proper columns. The macro uses regexp extract to pull the number after min and max from the stat string cast to bigint. It groups by row group ID and takes the overall min and max across all segments in that row group. The span column is just max minus min, the width of the value range that row group covers. 814 row groups, exactly what we predicted. 100 million rows divided by roughly 122,000 rows per group, rounded up. Here's what the zone maps actually look like for both columns. C1 on the left, C2 on the right. C1 first, row group 0, min 0, max about 122,000, span about 122,000, tight. Row group 1, min about 122,000, max about 245,000. Notice, row group 1 starts exactly where row group 0 ended. No overlap, no gap. Because C1 is sorted, each row group's range is a clean non-overlapping window. Row groups 0 through 3 all have maximums below 491,000. Row group 4, min 491,000, max 614,000. That's the only range that can contain 500,000. Every other group definitively skippable. Every group has roughly the same span as its row count, because C1 increments by 4 for every 4 rows. Row group 0, min 0, max nearly 100 million. Span, almost the full domain of C2. Row group 1, min 380, max nearly 100 million. Same story. Row group 2, 3, every single one spans nearly the full range. Every single row group for C2 spans almost the full domain. Any search value you pick, 500,000 or 1 million or 99 million, is almost certainly inside every range. There is no row group that can be proven to not contain the value. Nothing can be skipped. 813 out of 814 row groups can be skipped. DuckDB reads roughly 0.1% of the table, one row group, and finds 4 matches. 0. All 814 row groups must be read. Every single row in the table is touched. That's your 50x gap. explained completely by 2 numbers per row group. One practical setup detailed before the next module. DuckDB can work with more than one database file in a session. Attach means open another database file and give it a name. Use means make that attached database the default place for table names. Detach means close that attached database when you're done. So if the next module starts by attaching a tpch database and using it, that's all it means. Mount the file, switch into it, run the queries, then detach it later if needed. Try this yourself. Pause here and build this before moving on. Create a table with 2 float columns, one filled with random times 100, one filled with I divided by 10, an ascending sequence. Insert 1 million rows. Then run a filter on each column and compare the times. Use PRAGMA storage info to look at the stats column. Check the spans. The question to think about: what is it specifically about I divided by 10 that makes its zone maps tight? What would happen if you sorted the random column at insert time? Would its zone maps change? The answer is in the exercise file. Pause here and try it first. We create the floats table, 1 million rows. The ASVAL column rises in order from 0, 1 step per row, covering a span of about 100,000. The RNVAL column is drawn uniformly at random from 0 to 100. The filter on ASVAL finds 1 row instantly. Almost all row groups are skipped by the zone map. The filter on RNDeval returns 0 rows. Random data never hits an exact float. More importantly, the scan still touches every row group because the RNDeval zone map spans the full range in each group. The ASVAL column has a span of about 12,288 per row group. Each group covers exactly 1/9 of the range. Tight zone maps that let DuckDB skip 8 of 9 groups for the point lookup filter. The RNDeval column has a span of about 100 per row group, almost the full range of 0 to 100 in every group. No row group can be skipped for any filter value in that range. All 9 groups get scanned. This is the core lesson. Data insertion order determines zone map quality. ASCII-val was inserted in ascending order, so each row group contains a contiguous slice of the domain. RIND.val was inserted randomly, so every group contains values from across the full domain. Let's land this. DuckDB stores your table by column and by row group. Each column within row group has a zone map, just a min and a max. When a filter can't match a row group because the search value is outside the range, DuckDB skips the whole group without reading a single byte of actual data. The only thing you control is sort order at insert time. If you insert sorted data, your zone maps are tight. If you insert random data, they span the full domain. There's no create index needed here. The zone map is free, automatic, and always on. Up next, Module 04, Memory and the Buffer Pool.